Imagine for a moment you're holding two identical clocks. You put one on the kitchen table and take the other on a long train ride that zips around the planet at a good fraction of the speed of sound. When you bring it back and compare them, they're not quite the same. One shows a slightly different time. That sounds impossible at first. Time should be the same everywhere, right? But experiments and the theory built by Einstein show us that time is not an absolute river that flows the same for everyone. It's more like a stretchy fabric that can be tugged and slowed depending on motion and gravity. That's the heart of relativity, and it's the key to understanding how time travel, in the scientific sense, is already real in small, measurable ways. Let's start with the idea that changed everything: special relativity. Before Einstein, people imagined space and time as fixed and universal. But experiments in the late 19th and early 20th centuries, especially those trying to detect motion through the hypothesized ether, showed something strange. The speed of light in a vacuum appears the same no matter how you move. Einstein took that odd fact seriously and built a framework around it. The surprising consequences flow out so naturally you can almost taste them. If the speed of light is the same for every observer, then the idea of absolute time breaks down. Two people moving relative to each other will disagree about whether two events happened at the same time. That's called the relativity of simultaneity. A simple way to picture it: imagine a long train with a light bulb in the middle that flashes. Someone standing on the platform sees the light reach the front and back of the train at the same time only if the train is at rest. But if the train is moving, the light heading toward the front has to chase the moving front, while the light toward the back meets it sooner. Observers on the train and on the platform will disagree about whether the flashes at the ends happened simultaneously. That disagreement is not just philosophical, it's real and measurable. From relativity of simultaneity comes time dilation. Moving clocks run slow. If you're moving relative to me, my clock will say less time has passed for you than mine says for itself. The formula that describes this uses a factor called gamma, but you don't need the equation to see how it acts. At everyday speeds, walking, driving, flying, these effects are tiny. But as your speed approaches the ultimate limit, the speed of light, time stretches dramatically. At 80% of light speed, time for the traveler ticks about 1.7 times slower than for someone standing still. At 99.9% of light speed, a single week for a traveler could equate to many years for someone left behind. That's how forward time travel works. You go fast, you return to find more time passed elsewhere than you experienced. This is not just theory. Physicists have tested these ideas many ways. Muons, subatomic particles produced by cosmic rays striking the upper atmosphere, give us a vivid, natural experiment. Muons have a very short lifetime when at rest, roughly 2.2 microseconds, and you'd think the ones created high above Earth would disintegrate long before they could hit the ground. Yet billions of muons reach the surface every hour. The explanation is time dilation. These muons are moving at speeds near light, so from our frame they live longer. From their frame, the distance to the ground is contracted. Both explanations are two sides of the same relativistic coin. Particle accelerators perform controlled versions of this experiment, boost particles to high speeds, and their lifetimes lengthen exactly as special relativity predicts. You can also test time dilation with precise clocks. In 1971, physicists carried atomic clocks on commercial airliners around the world and compared them to clocks left on the ground. The results matched Einstein's predictions. The clocks that had flown ticked at slightly different rates, and the discrepancies agreed with the calculated effects from both motion, special relativity, and gravity, general relativity. The experiment is often told with a wink. People flew clocks on planes and confirmed time travel, because it puts relativity in a context anyone can imagine: airplanes and wristwatches. Now, gravity adds another layer. Einstein realized that gravity isn't a force pulling objects through space so much as a curvature of spacetime itself. Mass and energy tell spacetime how to curve, and curved spacetime tells objects how to move. Picture a stretched rubber sheet. Put a heavy ball on it and the sheet dips. A smaller marble rolls toward the heavy ball not because there's an invisible string pulling it, but because the surface beneath it is curved. That visualization helps with the motion part, but it also gives a feel for how time behaves near massive objects. General relativity predicts gravitational time dilation. Clocks deeper in a gravitational well tick more slowly than clocks further out. Stand on the ground, and your clock runs a hair slower than a clock on top of a tall mountain. The effect near Earth is small, but modern clocks are ridiculously precise. The Pound-Rybka experiment in 1959 was one of the first clear laboratory confirmations. They measured the tiny shift in the frequency of gamma rays moving up and down a tower, and found the shift matched the prediction from general relativity. Later, rockets carrying hydrogen maser clocks, the gravity probe experiment in 1976, sent clocks high above Earth to verify gravitational redshift with high precision. Today, optical atomic clocks are so sensitive that they can detect the difference in tick rate between two clocks separated by a vertical distance of just a few centimeters. That's practical time dilation on a tabletop scale. The need to account for relativistic effects is not an academic point. It's practical. You use it every time you tap a GPS navigation app. GPS satellites carry extremely accurate clocks, and because they are moving relative to an observer on Earth, and because they are in a weaker gravitational field than clocks on the ground, their clocks tick at a different rate. Special relativity predicts the satellite's clocks should tick more slowly because of their speed. General relativity predicts they should tick faster because they're higher up. The numbers don't cancel. The net effect is that satellite clocks would drift by about 38 microseconds per day if relativity weren't accounted for. That tiny amount, if uncorrected, would lead to navigation errors on the order of 10 kilometers each day. So GPS navigation literally depends on Einstein. If time can be stretched by motion or gravity, can those effects be arranged to actually create a machine for time travel, especially going back in time? That's where wormholes enter the conversation. Wormholes pop out of Einstein's equations as mathematical shortcuts connecting distant regions of spacetime. Picture a sheet of paper. Two dots at opposite ends of the sheet are far apart if you travel along the paper's surface. But fold the paper and poke a hole. If you can step through, the dots are now close. In relativity, this is more than an illustration. Certain solutions to Einstein's field equations describe what are called bridges or tunnels connecting two regions. The first to describe something like this were Einstein and Rosen in 1935. They found what we now call the Einstein-Rosen bridge. The problem is, those original bridges pinch off so quickly that nothing can pass through. For a wormhole to act as a tunnel you can travel, it needs to be traversable, a steady throat wide enough that remains open long enough for something to pass through. That's where things get tricky and fascinating. Physicists Kip Thorne and colleagues in the late 1980s asked, what would it take to hold a wormhole open? Their answer was unsettling. The throat would need matter with negative energy density, material that, in a specific technical sense, has less energy than empty space. Classical matter we experience, protons, electrons, light, doesn't do that. But quantum physics has a few tricks. A famous example of a quantum effect producing negative energy density is the Casimir effect. Put two very close, parallel metal plates in a vacuum and quantum fluctuations of fields between them are altered, producing a tiny attractive force, interpretable as a region of negative energy density between the plates. It's real and measurable, but the Casimir effect's negative energy is tiny and local. The wormhole throat would need large amounts of negative energy, arranged and stabilized in ways we don't know how to do. Quantum field theory also imposes constraints on how negative energy can be distributed, so the dream of building a macroscopic, stable wormhole looks wildly impractical with what we understand now. That doesn't stop relativists from doing thought experiments. Suppose, in that imaginative land, you have a traversable wormhole with two mouths. You keep one mouth stationary and take the other on a fast trip, or park it deep in a gravity well while the other stays high up. Relativistic effects mean that upon return, the traveling mouth could be out of sync in time with the stationary one, like jet-lagged tunnels. If you then step through the wormhole the wrong way, you could, in principle, emerge at a location and time earlier than you entered. That creates a closed time-like curve, a path through spacetime that loops back to its own past. These are the kinds of solutions to Einstein's equations that give physicists sleepless nights and philosophers a field day. You can build grandfather paradox scenarios out of them. Go back and stop your grandparents from meeting, and you run into logical contradictions. Nature may have ways to stop that from happening. Stephen Hawking proposed the chronology protection conjecture, a tongue-in-cheek reference to the idea that the laws of physics conspire to keep the timeline from being messed with. One potential mechanism is quantum instability near a would-be time machine. Calculations suggest that vacuum fluctuations, that ever-present bubbling of quantum fields, could pile up near a forming closed time-like curve, producing huge amounts of energy that would destroy the wormhole before it could be used to create paradoxes. But that line of argument involves quantum gravity, where the quantum world meets curved spacetime, and we don't yet have a complete, tested theory of quantum gravity. So chronology protection is an attractive idea, but not proven. Black holes give us another tantalizing real-world laboratory for extreme time dilation. If you could hover just above the event horizon of a black hole, the point of no return, time outside, and near that horizon would diverge dramatically. To a distant observer watching from far away, someone falling toward a black hole appears to slow down, their image redshifting and freezing asymptotically at the horizon. From the falling person's perspective, nothing particularly dramatic happens when they cross, until tidal forces rip them apart. A rotating black hole, a Kerr black hole, has even more exotic structure in its mathematics, including potential interior regions with weird causal relationships. But the safe, sober takeaway is that the universe offers places where the passage of time differs hugely depending on where you are and how you move. And these ideas aren't just in the realm of abstract math. Observational astronomy uses time dilation effects. Pulsars, rotating neutron stars that act like cosmic lighthouses, are precise clocks. When pulsars orbit massive companions or dance in tight binaries, their timing shows relativistic corrections, including gravitational time dilation and time delay effects. The Hulse-Taylor binary, pulsar, famously allowed physicists to probe general relativity in the strong field regime, and indirectly confirmed the existence of gravitational waves years before the direct detections by LIGO. Those timing measurements match the predictions of general relativity very closely, and they are another piece of evidence that Einstein's picture of spacetime is extraordinarily accurate. Let's return to something more immediate: the everyday experience of time travel to the future. Whenever a jet carries a clock faster than the ground, astronauts experience time slightly differently than people on Earth. The difference is small, microseconds to nanoseconds in most cases, but it's real. Astronauts aboard the International Space Station in low Earth orbit experience both effects. They're moving fast enough that special relativity slows their clocks, but they're also farther from Earth's center, so the weaker gravity speeds their clocks a bit. The net effect is that astronauts age a tiny bit more slowly than people on Earth, meaning they literally travel micrometers into Earth's future by the time they return. The difference is embarrassingly small for human drama, but it's no less real because it's small. Physicists have made relativity's predictions push and shove against experiments of ever finer precision. One of the neatest modern stories is the development of optical lattice clocks and ion clocks that achieve fractional uncertainties around 10⁻18 and better. That means if one clock ticks at a rate of 1, another clock might tick at 1 plus or minus a billionth of a billionth. With that sensitivity, simply raising one clock by a few centimeters changes the ticking rate in a measurable way. The gravitational potential difference between the two heights is enough to produce a detectable time shift. This opens curious possibilities. Geodesy, the measurement of Earth's gravitational field and even changes in local topography, can now be done by measuring time. Time told a story about the shape of Earth long before, but now time itself becomes a tool to sense elevations, groundwater, or the structure of underground features because gravity tells time how to flow. Let's be concrete about some classical experiments and results. The Ives-Stilwell experiment, done in the 1930s and refined since, measured the Doppler shift of light emitted by fast-moving ions and provided direct confirmation of time dilation. Particle accelerators provide a steady stream of confirmation. Particles accelerated to relativistic speeds live longer, and their trajectories and decays match the predictions precisely. Pound and Rybka measured the gravitational redshift in a Harvard Tower experiment by sending gamma rays up and down and measuring tiny shifts. Gravity Probe A rocketed a hydrogen maser upward, and clock comparisons matched the predicted gravitational frequency shifts. Haefel and Keating's flying clock experiment, though sometimes the way it's discussed gets simplified in pop culture, was a clear, direct demonstration that moving clocks and clocks at different altitudes disagree in the way relativity predicts. So when scientists say time travel is real, they usually mean two things. First, we have empirical, tangible phenomena in which time passes at different rates depending on motion and gravity. Second, the theory behind these phenomena suggests exotic geometries, wormholes, closed time-like curves, and other spacetime oddities could exist mathematically, and some of them would allow travel into the past or future. That's two very different claims. The first is solid and experimentally verified. The second is speculative, rooted in mathematics and blocked by practical and theoretical challenges that we don't yet know how to bypass. The push to understand whether the second claim could be realized focuses on several ways physics might forbid or allow time machines. One route is to look carefully at the types of matter and energy that classical general relativity allows. There are energy conditions in the theory, assumptions about how normal matter behaves, that exclude negative energy densities. Wormholes and many time machine constructions require violations of these conditions. But quantum mechanics is sneaky. It allows local violations, like those in the Casimir effect. So researchers ask, can quantum fields provide enough negative energy in the right arrangement and for a long enough time to hold open a macroscopic wormhole? As far as we know, the answer is no with our present techniques and understanding. But the field is alive. Questions about quantum inequalities, limits on how negative energy can be distributed, and about the stability of semi-classical constructions keep people thinking. Another road is to study what happens when general relativity and quantum field theory are fully combined into a working theory of quantum gravity. That's the big unknown. In a quantum gravity framework, spacetime itself will have new degrees of freedom, and new quantum constraints could either allow surprising possibilities, maybe some quantum fluctuations can stabilize a wormhole, or, more likely according to many physicists, produce mechanisms that prevent paradoxical constructions from being physically realized. It's worth noting that even if quantum gravity forbids time machines, the forbidding principle might be subtle and interesting, revealing deep aspects of how causality, information, and quantum mechanics intertwine. A related line of work investigates how semi-classical effects, the backreaction of quantum fields on spacetime curvature, play out near would-be time machines. Calculations often show that as a closed time-like curve is about to form, vacuum fluctuations grow without bound, producing energy densities that destroy the configuration. That's a technical path to chronology protection. But these calculations are tough, often requiring approximations, and rely on a regime where a full quantum gravity theory would be most appropriate. So they are suggestive rather than definitive. Beyond wormholes, there are other hypothetical constructs that could create unusual causal structures. Cosmic strings, for instance, are hypothetical one-dimensional defects in spacetime that could lead to weird paths if they existed and were arranged in certain ways. Rotating black holes in certain idealized solutions produce regions where causality is non-standard. The Kerr solution, which describes rotating black holes, allows for ergospheres and regions where frame dragging is so strong spacetime itself is being swept around. The mathematics of black hole interiors and the maximal analytic extensions of those solutions show technically possible closed time-like curves in some contexts. But again, nature might have built-in checks that prevent those mathematical oddities from being physically relevant. When you take astrophysical reality into account, dynamics, matter, stability, many of these exotic features likely collapse or hide behind horizons. One of the neat intellectual stretches you can do with these ideas is to treat time travel as a spectrum rather than a binary. At one end is trivial forward travel, the everyday, small, relativistic aging differences we measure and correct for. A bit further are dramatic but one-way voyages into the future. An astronaut traveling near light speed returns to a very different future. Further still, and much more speculative, are wormhole shortcuts that might create near-instantaneous jumps across vast distances, and perhaps backward time travel if the mouths are desynchronized. Each step requires more extreme conditions, higher speeds, stronger gravity, exotic matter, or new physics. Some recent experimental advances hint at how close we are to exploring these edges. The precision of atomic clocks means that tabletop experiments can probe gravitational potentials and time dilation at scales previously impossible. Optomechanical systems and quantum sensors are inching toward regimes where subtle quantum gravitational effects might become accessible indirectly. Large-scale observational astronomy, with ever more precise timing of pulsars, gravitational wave detections, and improvements in interferometry, probes gravity in stronger and more dynamic regimes. Each new measurement is a check on our theories and a possible crack through which new physics might peak. It's worth underlining the humility physicists have when they talk about time travel to the past. The mathematics of general relativity is permissive. It allows all sorts of geometries, including ones that produce causality loops. But physics is empirical at its core. Nature might allow some of those solutions, or it might hide them behind constraints we don't yet fully understand. The history of science is full of beautifully consistent mathematical possibilities that reality refuses to instantiate. Physics progresses by a mix of math, experiment, and a stubborn insistence on consistency with the rest of what we know. In conversations about time travel, people often get hung up on paradoxes, grandfather paradoxes, bootstrap paradoxes where information appears to have no origin. Those are valid puzzles, and they expose the tension between our intuition about cause and effect and the exotic possibilities permitted by the equations. Some proposed resolutions to such paradoxes involve self-consistency conditions. The idea that any actions taken in the past by a time traveler must be part of the history that already led to the time travel. Others suggest quantum mechanics might permit multiple histories or decohering branches, a la many worlds interpretations, so a paradox in one branch is resolved by branching into another. These ideas are speculative, yet they indicate rich intersections between gravity, quantum mechanics, and information theory. We can also think about the direction of time, the arrow of time, and why we seem to experience a single forward march from past to future. That arrow appears tied to entropy. The universe started in a highly ordered low-entropy state, and entropy increases as processes unfold. Relativity doesn't tell us why entropy behaves that way. It provides the geometric backdrop. But any discussion of time travel that tries to undo events must reckon with entropy and thermodynamics. The more you tinker with rearranging events, the more you run into statistical and thermodynamic constraints. Even if a time machine were built, pushing versus pulling entropy and keeping macroscopic causal consistency would be an immense challenge. Then there's the cultural and human angle. Time travel fascinates us because it stirs deep questions about fate, responsibility, and the structure of stories. Science fiction treats time travel as a mirror for exploring ethical and philosophical issues. What would you change, and should you? Would you save a loved one, or would you preserve the chain of events that made you who you are? These aren't physics questions per se, but they show why time travel captures the public imagination and why scientists are careful, when talking about it publicly, to separate what's experimentally grounded from what's speculative. We haven't talked about one more experimental piece that bridges ideas: the observation of gravitational waves by LIGO and Virgo. Those ripples in spacetime are not time travel devices, but they are a triumph of general relativity and our ability to detect tiny distortions in spacetime itself. When black holes collide, they send out waves that stretch and squeeze spacetime by minuscule amounts over kilometers. That we can measure such tiny shifts demonstrates both the predictive power of Einstein's theory and our technological ability to probe spacetime dynamics. It encourages confidence that if there were ways to realize more exotic spacetime configurations, wormholes, unusual topologies, we might detect indirect signs. One final, practical thought. You've already been time traveling your whole life. The moment you get into a fast car, climb a mountain, or strap into an airplane, your time has shifted relative to someone else. When your smartphone checks the time with satellite systems, or your bank reconciles ledgers across continents, they're implicitly accounting for relativity. That practical, commonplace thread is one of the coolest parts of the story. The stranger's math Einstein wrote down a century ago governs the tiny adjustments that let us navigate with GPS, synchronize networks, and build technologies that rely on precise timing. But beyond these daily conveniences, the deeper corners of the theory, the wormholes, the closed time-like curves, the tantalizing mathematical doors to the past, remain speculative and deeply interesting. They push physicists to ask better questions about quantum gravity, the interface of quantum field theory and curved spacetime, and how causality and information are preserved in extreme regimes. The search is a mix of careful measurements of clocks and particles, ambitious astronomical observations, and fierce theoretical work trying to stitch quantum rules to curved spacetime. Each frontier test, whether a lab table experiment measuring time dilation across a centimeter, or a radio telescope timing a pulsar already dancing around a compact companion, is another brick in the wall of understanding. So we stand in a peculiar place. On one hand, time travel is real in the sense that relativity makes it unavoidable and measurable. Clocks disagree, moving and high-speed life havers experience less proper time, and gravity alters the flow of time. On the other hand, the kind of time travel that lets you step into your own past, change events, and create paradoxes is a much thornier proposition. The math allows it, but physics, reality, has its own rules, constraints, and probably some built-in cautionary codes that prevent grand paradoxes from casually popping into existence. As we push forward, new technologies and observations will keep refining our picture. Better clocks, more precise particle experiments, improved gravitational wave detectors, and work toward quantum gravity will either reveal new pathways or shore up the barricades. Either outcome will be fascinating. Right now, the universe lets us sneak forward through time in tiny, measurable ways, teaches us to correct GPS by invoking the geometry of spacetime, and tempts us with mathematically coherent but physically challenging visions of tunnels through the cosmos. Keep your curiosity tuned. The story of time and the shape of reality is not finished, and each experiment is a conversation with the deep structure of the universe. Keep following that thread a little further, and you bump into one of the deepest puzzles in physics. General relativity and quantum mechanics treat time very differently. In Einstein's picture, time is part of the geometric fabric of the universe. Coordinate it, measure distances in time just like distances in space, and you can bend and stretch that fabric with mass and energy. In quantum mechanics, by contrast, time is a fixed backdrop that systems evolve against. The Schrödinger equation tells you how the quantum state changes with time, but there's no operator for time the same way there is for position or momentum. This simple mismatch becomes a real headache when you try to combine the two frameworks into a single theory of quantum gravity. It raises the so-called problem of time. What does time even mean when the entire universe is treated quantum mechanically? To make that feel tangible, imagine a movie. In ordinary quantum mechanics, you have a sequence of frames. Each frame is the state of the system at an instant, and an external clock ticks you forward through the frames. In general relativity, the movie is more like a single four-dimensional object. The frames are stitched together into a block, and different observers slice it into nows in different ways. Now ask, what is the quantum state of the whole movie? If you write down a quantum equation for the entire universe, you end up with something like the Wheeler-DeWitt equation, which famously doesn't contain an explicit time parameter. The mathematical object it produces looks frozen. That's weird because our everyday experience is all about change. Physicists have developed several strategies to recover an effective notion of time in these contexts, often by treating time as relational, something defined by change of one subsystem with respect to another. One of the clearest ways to see how time might emerge relationally is to consider entanglement. Suppose you have a complex quantum system and you split it into two parts, a clock subsystem and everything else. The Page-Wouters mechanism proposes that if the clock is entangled with the rest, then conditional on the clock showing a particular reading, the rest of the system will appear to evolve in a way that matches the Schrödinger equation. In plain English, if you are inside the universe and you check what the clock reads, the remainder of reality will look like it's changing with respect to that reading. You don't need an external time parameter. Time is what correlations between subsystems look like. The idea is abstract but powerful because it shows how an effective, operational notion of before and after can arise from a fundamentally timeless wave function by looking at relationships between parts. Entanglement and relational time are steps toward reconciling the two pictures, but they also bring the thermodynamic arrow of time back into the spotlight. Why does time seem to have a direction at all? Why can we remember the past and not the future? Why do eggs break but never spontaneously reassemble? The answer physicists give is statistical. The arrow of time is tied to entropy. Entropy is a measure of how many microscopic arrangements correspond to a macroscopic state. Low entropy states, an unscrambled egg, the early universe's remarkably smooth distribution of matter, are special and rare. Most configurations are high entropy, disordered arrangements. Thermodynamic processes tend to move systems from low to high entropy simply because there are vastly more disorderly microstates available. That statistical imbalance sets a preferred direction for processes and for our experience of time. This raises the next big question. Why was the early universe in such a low entropy state to begin with? Cosmologists have debated this for decades. One influential idea points toward inflation, the idea that a tiny region of space underwent an enormous, extremely smooth expansion very early on. Inflation can explain why the universe looks flat and uniform on large scales, and can produce the spectrum of small fluctuations that later grew into galaxies. But the initial smoothness itself is the low entropy condition that seeds the arrow of time. Gravity complicates things further because, unlike gas in a box, gravitational systems grow more ordered as clumps form galaxies and stars, while the overall entropy increases enormously due to the formation of black holes, which have tremendous entropy measured by their horizon areas. So the story of time's arrow is intimately tied to cosmology and to how gravitational degrees of freedom were set up in the early universe. Black holes sit at the intersection of thermodynamics, quantum theory, and spacetime, and they complicate our understanding of time in dramatic ways. In the 1970s, Jacob B. Kenstein and Stephen Hawking showed that black holes behave thermodynamically. A black hole's entropy is proportional to the area of its event horizon, and quantum effects make black holes radiate like a hot body, Hawking radiation. That radiation causes a black hole to slowly lose mass and evaporate over unimaginably long times. This process, however, gives rise to the famous information paradox. Quantum mechanics insists that evolution is unitary. Information about a system's initial state is preserved, even if scrambled, in its final quantum state. But naive calculations suggested that Hawking radiation is thermal and uncorrelated with what fell into the black hole, so when the black hole evaporates away, the information about its contents would be lost. That would violate unitarity and undercut the predictability that's central to quantum theory. Resolving the information paradox has been one of the most active fronts in theoretical physics. Over the last decade, there's been significant progress that suggests information is preserved, but the mechanics of how it escapes a black hole are subtle. Tools from quantum information theory and quantum gravity have converged, and new calculations of entanglement entropy, tracking how entanglement between the black hole and its radiation evolves, show a pattern called the Page curve. Entanglement rises as radiation begins, reaches a maximum roughly halfway through evaporation, and then decreases as information comes out. These calculations use ideas like replica wormholes and involve summing over non-trivial spacetime topologies. A simple image is that spacetime histories that look like wormholes connecting radiation to the interior contribute to the bookkeeping of information, allowing the radiation to carry subtle correlations that encode what fell in. The result is that, at least in these controlled setups, the end state can be consistent with unitarity and no information is lost, suggesting that deep relationships between geometry, entanglement, and quantum information are key. One of the bold ideas that emerged from trying to understand these relationships is the slogan ER equals EPR, put forward by Juan Maldacena and Leonard Susskind. ER refers to Einstein-Rosen wormholes and EPR to entangled particle pairs, from the Einstein-Podolsky-Rosen paradox. The conjecture is that entangled systems are connected by non-traversable wormholes in a deep geometric sense. That doesn't mean you can hop through an entangled pair to travel somewhere. These wormholes are not traversable in any way that would let information or people pass. But it hints that spacetime geometry and quantum entanglement are two sides of the same coin. If space is built from entanglement, then changing entanglement changes geometry. Conversely, geometry can encode patterns of quantum information. This viewpoint has energized research because it suggests that building spacetime from quantum bits might be the right route to quantum gravity. A neat outgrowth of that connection is the Ryu-Takayanagi formula in the context of holography, the ADS/CFT correspondence. It says, roughly, that the entanglement entropy of a region in a quantum field theory living on a boundary is proportional to the area of a certain minimal surface in the bulk geometry. Again, entanglement relates directly to geometric areas. People like Mark van Raamstonk argued that as you vary entanglement between parts of the boundary theory, the bulk geometry responds. Space literally pulls apart or knits together depending on entanglement. This gives a concrete mechanism for how classical-looking space might emerge from an underlying quantum description. Time, in these scenarios, is entwined with entanglement and information flow. Some conjectures even relate the growth of complexity, the minimal number of simple operations needed to prepare a quantum state, to geometric quantities like volume or action in the bulk. Leonard Susskind has suggested that the growth of complexity could be connected to why time seems to keep moving forward inside certain gravitational systems. While these deep theoretical developments might sound abstract, they have implications for the possibility of time travel too. One of the puzzles about closed time-like curves, CTCS, world lines that loop back to an earlier time, is how they affect information. In classical GR, such curves can be part of legitimate solutions, but they wreak havoc with causality. In quantum theory, people have studied models of quantum systems interacting with CTCs. David Deutsch proposed a model where quantum states entering a CTC must satisfy a fixed point condition. The state that goes into the curve must equal the state that comes out. That condition can resolve paradoxes by enforcing self-consistency in a quantum way, but it also introduces nonlinear behavior into quantum mechanics, which is alarming because linearity is central to quantum theory. Other formulations show CTCs could, in principle, dramatically enhance computational power, allowing solutions to problems classically thought intractable. So even hypothetical CTCs force us to reckon with deep principles about computation, information, and causality. Not all puzzling quantum experiments mean information is traveling backward in time. Take Wheeler's delayed choice experiment and quantum erasers. In these setups, the decision to measure one property or another can appear to retroactively determine how a particle behaved earlier. The striking part is how measurement choice seems to affect the past behavior of the system. But there's no paradox here in the operational sense. You can't use these setups to send signals into the past or change recorded classical outcomes. The apparent retrocausality is really a reflection of quantum correlations. The full statistical description of outcomes depends jointly on preparation and measurement choice, and only when you compare correlated measurement results does the counterintuitive pattern emerge. So quantum mechanics stretches our intuitions about cause and effect without giving you a neat time machine to send messages into yesterday. From the theoretical to the practical side, many of the spacetime geometries that allow backward time travel demand extreme physical conditions. Consider the Tipler cylinder. An infinitely long, massive cylinder spinning rapidly can, in the idealized equations, create closed time-like curves in the space around it. Or consider the GOT solution, where two ultradense cosmic strings passing by each other at high speed can produce paths that loop back. These constructions are mathematically consistent in general relativity, but physically suspect. They require infinite cylinders, or cosmic strings with enormous mass-energy densities and particular trajectories, and they typically ignore realistic material properties, instabilities, or quantum effects. The bottom line is that most of these exact solutions are either idealizations that can't be realized, or they would be violently unstable once you add realistic physics. Another recurring obstacle is energy conditions. Classical matter behaves in ways that keep spacetime well-behaved under many circumstances. Energy densities are positive, energy flows follow reasonable relations, and so forth. Many of the most exotic spacetimes, traversable wormholes, warp drives, and some CTC hosting solutions, violate these conditions, meaning they require negative energy densities or other pathological forms of matter. Quantum field theory allows local violations of classical energy conditions. Casimir plates provide a classic example where the vacuum between plates has slightly less energy than empty space. But quantum effects impose constraints too. There are quantum inequalities that limit how negative energy can be distributed in time and space, making it implausible to hold open a large, stable wormhole with known physics. So the exotic matter you'd need is not just unusual. It's something we don't know how to make in macroscopic quantities and might be forbidden by deeper quantum gravitational rules. Those deeper rules might be exactly what protects chronology. Stephen Hawking's chronology protection conjecture suggests that the laws of physics prevent time machines from forming. One argument in that direction is semi-classical backreaction. As a region of spacetime begins to evolve toward forming closed time-like curves, quantum vacuum fluctuations can grow without bound there, producing energy densities that blow up and prevent the process from completing. Technically, the stress-energy tensor of quantum fields could diverge near the would-be Cauchy horizon, the boundary beyond which predictability breaks down, and that divergence might destroy the geometry before time travel becomes possible. These calculations are messy and depend on approximations. They also probe the regime where we expect a full quantum gravity theory to be essential. Still, they offer a concrete mechanism by which nature could stamp out causal mischief before paradoxes arise. Observationally, we have no evidence of time travelers, wormholes, or other macroscopic violations of causality. That absence is not a proof. There are always reasons someone could hypothesize why such things would be hidden or rare, but it's a piece of data. Some people have even framed it as a form of Fermi paradox-like reasoning. If time travel into the past were easy and plentiful, we might expect to see signs of it. The lack of such signs suggests either it's impossible, extremely rare, or constrained by rules we don't yet comprehend. Philosophers and physicists have proposed consistency principles, like Novikov's self-consistency principle, which assert that events along closed time-like curves are constrained so that paradoxical actions are forbidden. In practice, that would mean any attempt to change the past would be thwarted by conditions that conspire to keep the history self-consistent. Thinking about causality and the block universe brings up deep philosophical terrain. Special and general relativity naturally fit with a block universe perspective, where past, present, and future are equally real and time is another coordinate like space. Our sense of now and the flow of time might then be emergent, tied to psychological processes and thermodynamics rather than a fundamental feature of physics. That view jostles with our everyday experience of becoming and decision-making. A related perspective focuses on information and complexity. Maybe the arrow of time and our sense of temporal passage are tied to the growth of computational complexity in a system, to how records and memories get created, and to the way causally connected subsystems accumulate correlations. These ideas are still tentative, but they hint that understanding time fully will require marrying physics, information theory, and something like the neuroscience of perception. Even if backward time travel remains blocked, the interplay of quantum information and gravity has practical implications elsewhere. Quantum computing, for instance, benefits from exploring the boundaries of what's allowed. Thought experiments that imagine access to CTCS show that if you had them, some problems would be knocked down in complexity. Tasks that take classical computers ages might be solved swiftly. That's largely a theoretical curiosity because the physical existence of CTCS is doubtful, but it illuminates deep links between computation, physics, and causality. Moreover, quantum information theory has given physicists new calculational tools, entanglement entropy, relative entropy, complexity measures, that are now central to probing black holes, holographic duality, and emergent spacetime. So even without time machines, there's tangible scientific progress. On the experimental front, the tools for probing these questions keep advancing. Atomic clocks get more precise year by year, pushing the boundary of where we can detect gravitational and relativistic effects. Interferometers like LIGO and Virgo have already opened the gravitational wave window. Future upgrades and new detectors will probe stronger field and more complex gravitational dynamics. Laboratory efforts to put larger masses into quantum superpositions, working towards so-called macroscopic quantum states, could test whether gravity acts quantum mechanically or somehow resists superposition, a proposal championed by people like Roger Penrose who have speculated about gravity-induced collapse. While such experiments are immensely difficult, progress in cryogenics, isolation, and quantum control makes formerly fantasy-level tests into plausible long-term projects. Each new precision experiment pushes our empirical foothold in regimes where quantum gravity effects might show up indirectly. A particularly intriguing experimental direction is trying to detect subtle signatures of spacetime topology or geometry that aren't obvious in everyday life. For instance, people have considered whether microscopic wormholes or non-trivial topologies in spacetime could leave imprints on the cosmic microwave background or in the pattern of high-energy cosmic rays. So far, there's no compelling evidence, but the search is scientifically healthy. Casting a broad net means the data can either reveal surprises or put tighter limits on exotic physics. At the same time, tabletop experiments testing semi-classical gravity, how quantum fields backreact on classical spacetime, are becoming feasible in principle. If measurable deviations from the predictions of semi-classical approximations were found, it would be a genuine hint at the physics that lies beyond our current theories. There's also a social and cultural dimension that's worth mentioning because it colors how science gets communicated. Time travel is a storytelling goldmine. It raises human questions about regret, responsibility, and fate. Scientists have to work hard to keep public conversations grounded in what's empirically supported, while still celebrating the imagination that drives speculative thought. That balance is healthy. Sci-fi inspires scientists and scientists bring rigor to sci-fi. It's useful to separate three things when people talk about time travel: the proven everyday effects of relativity, which are real and measured; the speculative but mathematically allowed solutions in general relativity, which are theoretically interesting but likely unphysical; and the currently impossible engineered scenarios that would require new physics or extraordinary resources. Treating them distinctly helps honest public engagement and keeps us clear about where imagination ends and evidence begins. One more technical pathway that keeps cropping up in discussion is the role of topology change in spacetime and how quantum mechanics might permit or forbid it. In classical general relativity, topology is usually fixed. The global shape of space doesn't change with time in ordinary solutions. Quantum gravity, however, might allow spacetime to fluctuate in topology at the Planck scale, tiny, momentary wormholes flickering in and out of existence. Whether such spacetime foam could sum up to produce macroscopic effects is uncertain, but the possibility fuels a lot of theoretical work. If topology can change, then so can causal structure in exotic ways. Whether those microscopic events average out to ordinary macroscopic causality or seed surprising phenomena is an open, technical question. Finally, as we probe deeper into these issues, we keep bumping up against the same big truth. We don't yet have a complete, experimentally confirmed theory of quantum gravity. The ways time, information, and geometry interlock at the smallest scales remain mysterious. What we do have are powerful hints. Entanglement looks central to building space. Semi-classical analyses suggest mechanisms, like backreaction, that protect causality, and thought experiments push us to clarify assumptions and boundaries of validity. So the path forward is both experimental and conceptual. Better clocks, more precise gravitational probes, clever tabletop quantum experiments, and theoretical breakthroughs in understanding how quantum information maps into spacetime geometry. All of these are the kind of investigations that, over the long run, will tell us whether the universe has strict rules that forbid practical time travel into the past, or whether it secretly allows narrow, controlled loopholes that reconcile paradoxes in ways we haven't yet imagined. If you want to keep nudging the problem, one particularly fertile mental experiment is to ask: suppose a tiny, carefully engineered wormhole were somehow made and stabilized. What would you need to do to make it into a time machine, and what paradoxes would you face? That question forces you to combine general relativity, quantum field theory, quantum information, and thermodynamics into one messy calculation. It's the sort of calculation that surfaces precisely the kinds of constraints people keep finding: energy conditions, quantum inequalities, dynamical instabilities, and entropy bookkeeping. Working through such an exercise in a simplified model is a great way to see how real physics resists simple sci-fi scenarios, and how the various pillars of modern physics talk to each other when pushed to their limits. Okay, pick up the mental exercise where we left off. Imagine somehow you've built a tiny traversable wormhole. What would you actually have to do to turn that creature of equations into a time machine, and what punches does reality throw back? Walking through that makes the physics that breaks reality feel concrete, and it exposes why most serious physicists end up skeptical about practical backward time travel, even if they remain thrilled by the math. First, the throat. For a wormhole to be traversable, you need a stable tunnel, something that doesn't pinch off the moment you try to crawl through. Classical matter, the stuff made of atoms that we handle every day, likes to have positive energy density. You can pile energy into a region, and it increases the curvature of spacetime in predictable ways. The trouble is that to hold a wormhole throat open, you typically need the opposite: negative energy density, the kind of thing that pulls instead of pushes. That sounds like magic, but quantum physics gives us tiny, real examples. The Casimir effect, where two metal plates sitting a hair's breadth apart experience an attractive force because the quantum vacuum between them is a bit different from the vacuum outside, is one such effect. In the space between the plates, the energy of vacuum fluctuations is slightly lower than elsewhere. You can think of it as a small patch of negative energy density. So could you tile up Casimir plates and make a wormhole? Not really. The Casimir negative energy is tiny and fragile. More importantly, quantum field theory doesn't allow you to accumulate negative energy arbitrarily for arbitrarily long. There are quantum inequalities, technical but intuitive if you think about them this way. You're allowed to borrow negative energy from the vacuum, but you have to pay it back quickly, and the amount you can borrow decreases as you try to spread it over larger regions. If you try to make a macroscopic patch of negative energy that's sustained long enough to support a human-sized wormhole throat, the inequalities say you'd need absurdly concentrated and short-lived bursts far beyond any engineering we can imagine. It's like trying to keep a bank account below zero indefinitely with a series of tiny, short-lived IOUs that force you to repay immediately. The bookkeeping makes the whole enterprise impossible beyond microscopic scales. Then there's stability. Even if you could engineer a throat with suitable negative energy, quantum fields living on that background will react. The more you arrange spacetime in the odd pattern needed for closed causal loops, the more the vacuum itself starts to behave badly. Fluctuations pile up. Many semi-classical calculations show that as you approach configurations that would allow closed time-like curves, the energy in these vacuum fluctuations blows up near the boundary where causality would fail. That pileup would backreact on the geometry. In other words, the wormhole spacetime would be wildly altered by its own quantum fields, probably destroying the delicate arrangement before you could exploit it to send someone into the past. Stephen Hawking called this idea chronology protection. The notion that the quantum fields conspiring around possible time machines act as a kind of watchdog, making sure the timeline doesn't get messed up. You can see the logic practically if you picture stirring a pot. Small ripples are fine, but if the brew of quantum fluctuations starts to resonate with the geometry you created, it's like pushing the pot into a boom of sloshing water that spills everything out. Those instabilities are messy to calculate. They live where classical general relativity hands off to quantum field theory on curved backgrounds, precisely the regime where you'd want a full quantum gravity theory to take over. So the semi-classical arguments are suggestive rather than final, but they're persuasive enough that most researchers think nature, probably, has ways to shut down macroscopic time machines. There are other classic would-be time machines whose problems are instructive. Consider the Tipler cylinder. An infinitely long, extremely dense spinning cylinder produces, in idealized mathematics, closed time-like curves outside it. The trick is infinitely long. That's a red flag. Real objects are finite, and when you make the cylinder finite, other effects crowd in. The edges radiate gravitational waves, instabilities appear, and anything you actually build collapses into something boring before you ever get a working time loop. Similarly, cosmic strings, hypothetical one-dimensional defects that might form in the early universe, can, under some bizarrely contrived motions, allow closed time-like curves. But cosmological searches and theoretical constraints make cosmic strings with the necessary properties seem unlikely, and realistic corrections make CTC production practically impossible. The Alcubierre warp drive, which made a splash in public imagination, exposes related issues. Mathematically, you can write down a spacetime that squeezes space in front of a ship and expands it behind, letting the ship move effectively faster than light relative to distant observers while locally staying in a region of flat spacetime. But the construction demands negative energy, and even worse, the original formulation required astronomical quantities of it, plus unstable energy flows that would likely produce violent effects at the ship's edges. Later work softened the energy requirements somewhat and found ways to reduce the worst pathologies, but the need for exotic matter again appears. The pattern keeps repeating. The math allows startling things, but they demand matter and energy distributions that either violate known quantum inequalities or are unstable in realistic settings. Not all theoretical work ends in dead ends. In recent years, some clever constructions in the context of ADS/CFT, that's a precise dictionary between certain quantum field theories and spacetimes with a negative cosmological constant, have shown that quantum effects can, in principle, make wormholes traversable. The Gauss-Jafferis wall protocol demonstrated that by introducing a certain quantum coupling between the two sides of an eternal black hole in ADS spacetime, you can open a brief window where a signal can go from one side to the other through the wormhole. Crucially, the mechanism uses quantum effects to produce just the right negative energy pulse to permit traversal. It's a big conceptual step because it proves a principle. Quantum matter can alter geometry in subtle ways that temporarily permit what classical GR forbids. But that success comes with caveats. The wormholes in these constructions live inside a very special spacetime and depend on particular boundary conditions and quantum couplings that are easy to specify in the ADS/CFT laboratory, but hard to map onto our universe, which is not asymptotically ADS. Also, these traversable wormholes are non-traversable for macroscopic objects in the naive sense. They can carry quantum information or a small signal for a brief moment. In short, these results are powerful theoretical demonstrations that quantum effects can shift the causal structure of spacetime, but they fall far short of giving us a blueprint for building a human-sized time machine on Earth. There's another angle people like because it ties to computation. What if closed time-like curves existed as part of quantum processes? The consequences for computation are dramatic. You can, in many models, solve computational problems thought to be extremely hard or even intractable. That suggests the presence of CTCS could collapse computational complexity hierarchies. Some researchers view that as a hint that physics forbids CTCS, because otherwise it would disturb the elegant structure of computation in ways that seem inconsistent with everything else we observe. It's not a formal prohibition, but it's the kind of cross-disciplinary constraint that makes a physicist pause. Physics has to be consistent with both the rest of physics and with information theory. What about searching observationally for wormholes or other signs that spacetime has weird topology? Astronomers have put serious effort into looking for footprints. A static traversable wormhole between two distant regions would produce a distinctive gravitational lensing signature. Light passing near a wormhole mouth can produce multiple unusual images, or rings with odd flux ratios, and time delays that don't match ordinary lensing by a galaxy or black hole. People have combed through lensing surveys looking for anomalies, and while some curious candidates pop up, none survive scrutiny as convincing wormhole signatures. Gravitational waves add another probe. The merger of two exotic compact objects could generate waveforms with echoes or deviations from the clean black hole merger signals LIGO and Virgo predict. Some papers over the years have claimed tentative evidence for such echoes, but those claims either evaporate with better data or depend on analysis choices that are controversial. In short, so far the sky has not produced a dong of a wormhole bell. Another astrophysical place where the math suggests odd causal structures is the rotating black hole. The idealized Kerr solution, the textbook rotating black hole, has an inner region where the coordinate roles of space and time get mixed up, and in the extended mathematical solution, even includes closed time-like curves. If you were an explorer falling in that idealized world you could, in principle, find yourself in odd coordinate regions or even move toward another universe. But realistically, astrophysical black holes are messy. They form from collapsing matter, rotate, accrete, interact with surrounding fields, and develop instabilities at the inner horizon region. One key issue is mass inflation. As infalling matter and radiation pile up near the inner horizon, their energy as seen by a local observer becomes enormous, causing the inner horizon to become singular and crushing any smooth passage. So the parts of the Care solution that suggest time machines are almost certainly artifacts of assuming a perfectly clean, eternal black hole, not the messy astrophysical beasts we actually find. There are also broad theorems in general relativity that work against traversable macroscopic topology changing or naked causal loops. The topological censorship theorem says, roughly, that under reasonable conditions, energy positivity and global hyperbolicity, spacetime topological features like wormholes can't be seen by observers who start and end in asymptotically flat regions. You can have non-trivial topology in principle, but observers can't probe it unless horizons hide it. That again pushes traversable wormholes into the realm of the highly contrived. If you go microscopic, Planck scale tiny, quantum gravity likely makes spacetime foamish, with topological fluctuations popping in and out of existence. Those microscopic wormholes could be important for the deep quantum structure of spacetime, entanglement, and information flow. But they're too small and short-lived for travel, and probably too scrambled for coherent signals. The funny thing is that such microscopic features might still leave faint fingerprints, modified dispersion relations for particles at extremely high energies, or minute deviations in the propagation of light over cosmological distances. People have looked for such signatures in gamma-ray bursts and the cosmic microwave background and set tight bounds. So while spacetime foam remains a theoretical possibility, its macroscopic exploitation looks unlikely. Another direction that has attracted attention is analog gravity, making laboratory systems whose equations look like those of fields on curved spacetimes. You can build an event horizon for sound in a flowing fluid or for light in a nonlinear optical medium. Experiments with Bose-Einstein condensates, optical fibers, and water waves have reproduced aspects of Hawking radiation, mode mixing, and superradiance in controlled settings. Those analogs don't make wormholes or time machines for real, but they let physicists study how quantum fields behave near horizons and in curved backgrounds, including the effects of backreaction and dissipation in situations we can experiment with. That empirical input helps test semi-classical ideas, whether vacuum fluctuations can pile up and destabilize a would-be time machine, in a setting where controlled measurements are possible. Let's pivot for a moment and think about constraints coming from cosmology and large-scale structure. If the early universe created networks of defects with the right properties, cosmic strings, domain walls, etc., some spacetime regions might have had odd causal structures. But cosmological surveys, maps of the microwave background, large-scale galaxy distributions, and gravitational lensing studies place tight limits on massive defects. Inflation itself, the leading paradigm for the early universe, tends to iron out irregularities and dilute exotic topological features. So even if time machine-friendly features can mathematically exist, it seems nature either didn't produce them in abundance or, if it did, they were soon hidden or destroyed. A particularly interesting modern twist is the way quantum information has re-entered the geometry conversation. Entanglement isn't just a quirky quantum property. In many modern approaches, it looks like the glue that knits spacetime together. Ideas like ER equals EPR, the conjecture that entangled states are somehow connected by non-traversable wormhole geometry, suggest that the connections between different parts of space are fundamentally informational. That's deep because if geometry is emergent from entanglement, then changing entanglement patterns changes geometry. Some recent work has shown how carefully engineered entanglement manipulations can produce effects in dual gravitational descriptions that mimic opening up communication channels. Again, these are in special, highly symmetric contexts, but they show an exciting possibility. Even if traditional wormholes are impossible, perhaps quantum information techniques could create effective shortcuts for information without violating causality. All of this reinforces a broad theme. The mathematical permissiveness of Einstein's equations doesn't automatically translate to physical permissiveness. Equations allow wild gardens of possibilities, but the garden is not the same as the climate. Matter types, quantum laws, thermodynamics, and stability constraints, the full climate of physical law, decide which plants can actually grow. Time machines, in most constructions we understand, are like orchids that demand exotic soils, negative energy, exact humidity, fine quantum tunings, and precise light cycles, stability against fluctuations. The environment we live in doesn't seem to provide those conditions in any robust, repeatable way. That said, the inquiry is far from sterile. Trying to build a time machine on the blackboard forces physicists to sharpen many concepts. What do we mean by causality? How does quantum information leave a black hole? How do semi-classical approximations break down? Those sharpenings have already given us new tools. The recent insights about entanglement entropy, replica wormholes, and the page curve were motivated by trying to resolve paradoxes about information and time in black hole evaporation. Problems that sit squarely at the intersection of general relativity and quantum theory. They didn't give us a time machine. They gave us a better understanding of how geometry and information interlock. The fact that those same tools then produce toy models where small traversable windows open in wormholes is evidence of real progress in the problem, even if practical time travel remains science fiction. There's also a human problem angle that's easy to forget. If you imagine that some future civilization engineered a functioning, macroscopic closed time-like curve, what happens to questions of agency, law, and responsibility? That's not physics per se, but it matters to society's thinking in long-term terms. Many philosophers and ethicists have already used the time travel thought experiments to explore consistency, free will, and moral responsibility. Those discussions are useful because they force us to be precise about what changing the past would even mean in a physical theory that has records, entropy, and information constraints. So what should you take away from this next stretch of the story? The math tells you that the universe permits astonishing geometries. The experiments tell you that time is flexible in small, measurable ways. And the tension between the two is the frontier where many of the most interesting problems lie. You can't build a grandfather paradox device in your garage with known physics. But you can do real experiments that probe the boundary between quantum mechanics and curved spacetime. Experiments that will teach us about entanglement, decoherence, and whether semi-classical backreaction is the final word on chronology protection. And those experiments are happening. Better clocks, more sensitive gravitational wave detectors, analog gravity labs, and quantum control experiments with larger and larger masses are all chipping away at the fog. What might a decisive experiment look like? One route is improving our ability to test semi-classical backreaction directly. If tabletop or laboratory analogs could show that vacuum fluctuations near configurations that mimic forming closed time-like curves produce substantial backreaction, that would strengthen the case for chronology protection. Another route is pushing gravitational wave and lensing surveys to detect or rule out exotic compact objects with greater sensitivity. A third is the continued refinement of quantum gravity toy models, ADS/CFT calculations, quantum error-correcting interpretations of spacetime, and entanglement-based constructions, which can tell us whether traversability is allowed in principle and under what constraints. Meanwhile, the technological spin-offs are already real. Precision timing, quantum sensors, and control of quantum fields in engineered backgrounds feed into navigation, communications, meteorology, and fundamental metrology. The same techniques that inform debates about time and causality also power better GPS, more sensitive tests of fundamental constants, and quantum technologies. Even if we never build a time machine, the work of thinking about them makes practical contributions. Keep asking the questions, because even if time travel to the past ends up forbidden, the attempts to understand why will reveal deep facts about the universe. How geometry and entanglement interact, how information is conserved in extreme situations, and how quantum fields behave when stretched by gravity. Those are the kinds of lessons that change how we think about everything from black holes to the cosmological history of the universe. The drama of time travel is a great hook, but the payoff is broader. Better theories, better experiments, and a richer picture of what reality actually allows. If you step back from the big words and the textbooks, one of the clearest ways to think about where the science stands is to ask, what exact physical ingredient keeps getting in the way of building a time machine? That question is more practical than dramatic, and it's what many researchers actually try to answer. The recurring culprits are a handful of related constraints: the need for negative energy in large, sustained amounts, quantum limits on how negative energy can be arranged, instabilities that amplify tiny quantum fluctuations into destructive backreaction, and the messy realities of anything that actually forms dynamically in our universe. Those are technical phrases, but the ideas behind them are easy to picture with familiar analogies. Think of negative energy like a kind of anti-weight. Ordinary mass and energy are like adding weight to a trampoline and making a dip. Negative energy would be the odd case of pushing up and making a bump. Wormholes and many warp drive ideas want that anti-weighting in precisely the right place, so that spacetime curves in a way that makes a tunnel or a bubble. Quantum physics does offer tiny glimpses of anti-weight. The Casimir effect between two plates is a measured instance, where the vacuum between the plates has slightly lower energy than the vacuum outside. But the Casimir negative energy is like a toy model or a coin in your pocket. Neat and demonstrable, but far, far too small and delicate to hold open anything the size of a person. Quantum inequalities say you can borrow negative energy, but the bank's rules are strict: short-term, tiny amounts only, and you must repay quickly. Those bookkeeping laws of nature are what make the exotic geometries so stubborn to realize. The next practical barrier is instability. Even if you could achieve the right energy distribution for a moment, quantum fields living in that region don't sit quietly. Vacuum fluctuations, the spontaneous, jittery appearances and disappearances of virtual particles, respond to unusual spacetime geometries. In many calculations, those fluctuations pile up near the edge of a would-be time machine, and their energy increases dramatically. That large, piled-up energy then curves spacetime back, often in a way that closes off the dangerous path. The semi-classical calculations that show this pileup are not the final word. You'd want a full quantum gravity answer, but they provide a concrete mechanism by which the universe fights back against time travel-friendly setups. It's like trying to balance a tower of plates. You can stack a few, but once the top ones start to vibrate, the tower collapses unless you have a way to damp the motion. Vacuum fluctuations are that vibration. A strand of theoretical work that's been particularly productive lately sidesteps some of the rough edges by working in controlled settings, where both sides of the problem, geometry and quantum matter, are tractable. That's where ADS/CFT and low-dimensional models enter. ADS/CFT is a mathematical duality that relates a quantum field theory, no gravity, living on a boundary, to a gravitational theory in a higher dimensional bulk, spacetime, with negative cosmological constant. In that setup, researchers found striking constructions where quantum interactions between the two boundary theories can momentarily make the wormhole in the bulk traversable. The breakthrough work by Gao, Jafferis, and Wall showed that a specific kind of simple quantum coupling produces a negative energy pulse in the bulk that opens a brief window for information to pass through. The striking thing is conceptual. Quantum effects can do work on geometry in ways that temporarily alter causal structure. But those wormholes live in special spacetimes and rely on boundary conditions we don't have on Earth, and the traversable windows are tiny. What the result gives us instead is a proof of principle. Quantum matter can change geometry enough to permit short-lived causal shortcuts under the right conditions. That same line of thinking leads to remarkably intuitive analogies between wormholes and quantum teleportation. Quantum teleportation is a real protocol in which an unknown quantum state is transferred from one location to another, using an entangled pair and classical communication. In some holographic setups, teleportation corresponds in the dual gravitational picture to sending a signal through a wormhole when the right coupling is applied. It's not literally turning teleportation hardware into a tunnel you could crawl through, but it helps clarify the idea. Entanglement patterns and the right control operations can move quantum information in ways that have a simple geometric interpretation. That correspondence is one reason people get excited. It suggests spacetime geometry and quantum information are two aspects of the same deeper story. Shifting from geometry to information opens a different set of constraints and possibilities. If closed time-like curves were physically available, they'd be immensely useful for computation. Several mathematical models show that CTCS could dramatically reduce the difficulty of solving certain computational problems. In some formulations, they would collapse complexity classes and let you solve NP-hard tasks quickly. That observation is both tantalizing and worrisome. It suggests that if CTCS are real, they could have far-reaching consequences for what tasks are physically feasible. Conversely, the globe's stability and the apparent structure of computational complexity in nature provide an indirect argument that something prevents easy access to CTCs. It's not a rigorous exclusion, but it's the kind of cross-check physicists appreciate. Physics has to hang together across different domains, from gravity to information theory. Quantum formulations of time travel attempt to capture these ideas in concrete models. David Deutsch proposed one model in which a quantum system that travels through a CTC must satisfy a self-consistency condition. The state entering the curve is the same as the state exiting it, after interacting with external systems. That constraint can resolve paradoxes like the grandfather paradox by forbidding inconsistent histories. The system state simply settles into a fixed point that avoids contradiction. But Deutsch's model introduces nonlinear behavior into quantum mechanics when you condition on CTC interactions, and nonlinearity is a big red flag because it wrecks many cherished results in quantum theory. Other models, like the one proposed by Seth Lloyd and collaborators, model CTCS as post-selection processes, PCTCS, where certain outcomes are conditioned upon. Each approach teaches us about how quantum theory copes with self-consistency and causality, and each has consequences for computation and information flow. None provides a simple path to building a time machine, but they have sharpened the questions about what must change in our theories for paradoxes to disappear. Black holes give another rich laboratory where time, information, and geometry tangled in knotty ways over the past decades. The black hole information paradox forced physicists to invent new conceptual and technical tools. One of the surprising outcomes of those efforts is that the same kinds of geometrical tricks we invoke for wormholes, replica wormholes, entanglement islands, and so on, appear in calculations that recover unitary evolution for black hole evaporation. The Page curve, which tracks the growth and eventual decline of entanglement entropy between an evaporating black hole and its radiation, had been a signpost for information conservation, or loss. Recent computations that include non-trivial saddle points in the gravitational path integral, geometries that look like wormholes connecting different replicas of spacetime, reproduce the Page curve consistent with unitarity. The upshot is that geometry and quantum information are more deeply linked than we thought, and processes that once seemed to leak information might be reconciled when you account for these non-perturbative geometric contributions. That conceptual progress is exciting for two reasons. First, it suggests that spacetime topology and connectivity can emerge directly from quantum information considerations. Second, it shows that wormhole-like objects can play information-theoretic roles without being traversable in the usual sense. The replica wormholes that help fix the Page curve do not give you a way to send a messenger into the past. Instead, they encode how information about the black hole's interior becomes encoded in the outgoing radiation in a way compatible with quantum mechanics. It's a different perspective on wormhole, not a tunnel for people, but a bookkeeping device in the gravitational path integral that preserves unitarity. That perspective is an important conceptual check. Geometry can help resolve information puzzles without enabling causal mischief. On the experimental front, the steady advance of precision measurement techniques is providing new levers for testing these deep questions. High-performance atomic clocks have advanced to the point where raising one clock by a centimeter produces a measurable difference in tick rate due to Earth's gravity. Networks of clocks distributed around the world or sent to space can test relativistic predictions in regimes we couldn't access before. Atom interferometry experiments can sense minute accelerations and gravitational gradients, opening paths to probe tiny gravitational effects on quantum systems. If semi-classical backreaction plays the role chronology protection suggests, there may be laboratory analogs where vacuum fluctuations and their backreaction are measurable. Analog gravity experiments, using Bose-Einstein condensates, nonlinear optical fibers, or flowing fluids to mimic aspects of curved spacetime, let physicists study Hawking-like radiation, horizon phenomena, and mode mixing under controlled conditions. Those setups won't build a time machine, but they do let us test whether exotic geometric configurations generically induce runaway backreaction, or whether engineered couplings can tame the behavior, as in the ADS/CFT traversability protocols. Another experimental frontier is pushing quantum coherence to larger, more massive systems. If we can put heavier and heavier objects into genuine quantum superpositions, we'll start probing whether gravity behaves quietly as a quantum field or whether it resists superposition in some way. Roger Penrose and others have speculated that gravity might cause wave function collapse for sufficiently massive superpositions, and experimenters are working toward masses where such exotic collapse models could be decisively tested. The outcomes of those experiments will inform the question of whether gravity can be consistently quantized in the ordinary quantum sense, and that feeds back into our understanding of whether spacetime topology and causal structure can be coherently manipulated at the quantum level. Astronomical observations also weigh in. If macroscopic wormholes or other causal anomalies were common, they might leave characteristic signals. Peculiar gravitational lensing patterns, unusual time delays between multiple images, or gravitational wave signatures inconsistent with ordinary black hole mergers. People have combed through lensing surveys and gravitational wave catalogs searching for oddities. So far, nothing compelling has emerged. That absence of evidence is not a proof that exotic geometries never happen, but it does place meaningful limits on how common they could be. Similarly, pulsar timing arrays, which look for correlated shifts in pulse arrival times from millisecond pulsars across the sky, give us sensitivity to low-frequency gravitational waves and could, in principle, detect signatures from exotic cosmic strings or background topologies. Cosmological data, especially the cosmic microwave background, also constrains dramatic early universe features that would seed large-scale causal oddities. If you like to play through thought experiments, one instructive one is a hybrid of the twin paradox and a traversable wormhole. Imagine two twins, Alice and Bob. Alice boards a ship and accelerates to relativistic speeds for a long journey. When she returns, she's younger than Bob, ordinary special relativity time dilation. Now suppose there's a tiny, quantum-engineered wormhole with two mouths separated in space, but not necessarily in time. If one mouth takes a high-speed trip and returns, the mouths could be desynchronized in time due to relativistic effects. That sets up the textbook scenario for potential backward travel. Enter one mouth and exit at an earlier time at the other mouth. Working through that scenario reveals where the constraints bite. You need to hold the mouth open against collapse. You need to prevent the vacuum fluctuations from blowing up. You need to manage the negative energy distributions and their quantum inequalities. Each physical constraint you put in quickly turns the scenario into a highly contrived engineering problem rather than a feasible plan. The mental exercise is useful, though. It highlights precisely where our theories impose heavy costs. Philosophical wrinkles keep bubbling up, too. The block universe picture, where past, present, and future all exist in a four-dimensional block, makes time travel less strange. Moving a person's world line around inside the block just changes which part of the block they occupy. But that perspective can feel counterintuitive because it seems to rob us of dynamism and choice. The Novikov self-consistency principle offers a different tack. If closed time-like curves exist, then events on those curves must be self-consistent. You can travel to the past, but your actions were always part of that past. That avoids paradoxes at the cost of restricting possibilities. Quantum approaches add nuance. Perhaps histories decohere into branches or fixed points that enforce consistency while still allowing probabilistic outcomes. These are philosophical moves informed by physics, and they show how understanding time travel requires thinking about both the mathematical structure of physical laws and about what we mean by cause and effect. All of this brings us back to the productive tension at the heart of modern research. General relativity says unusual causal structures are mathematically possible. Quantum mechanics suggests mechanisms that either enforce consistency or dramatically modify the picture. Reconciling those two frameworks continues to be the grand open problem. But the attempt is not idle speculation. Every piece of progress, whether a better clock, a tabletop test of semi-classical backreaction, or a new theoretical tool connecting entanglement to geometry, is a step toward a clearer picture of whether the universe allows controlled causal loops or decisively forbids them. There's a human and technological upside to all this arcane-sounding work. Precision timing technologies born of these studies are already practical. Navigation, telecommunications, and financial systems all rely on accurate timekeeping that must account for relativistic effects. Quantum control techniques developed for probing information flow in gravity are finding applications in quantum computing and sensing. The effort to push macroscopic quantum experiments forward supports progress in cryogenics, vibration isolation, and noise suppression, all of which have downstream uses. So the science of time, whether ultimately yielding time machines or strict protection of chronology, is directly spawning tools that reshape technology. If you want a concrete sense of where small, real experiments might give big conceptual payoffs, watch the overlap between three areas: atomic clocks and interferometers, analog gravity labs, and quantum optomechanical experiments with increasing mass. Those three fields converge on the semi-classical regime, where quantum fields interact with classical spacetime curvature. By tightening the experimental constraints in that regime, measuring how vacuum fluctuations respond to engineered geometries, observing the onset or absence of backreaction effects in analogs, and testing how gravity acts on quantum superpositions of bigger masses, we can begin to convert speculative mechanisms into robust evidence either for or against certain forms of chronology protection. Even a null result, showing that negative energy effects remain too constrained at scales where we can test them, is a powerful clue. Negative results sharpen theory, telling us which mathematical avenues are merely curiosities and which deserve further attention. Another route worth keeping an eye on is the development of quantum networks and distributed entanglement at scale. As labs create larger entangled states between distant nodes, we'll explore more complex patterns of information flow that could mimic, in some sense, the information-moving behaviors that wormholes represent in theoretical models. Those network experiments won't make travel to the past possible, but they will test whether entanglement can be harnessed in more exotic, geometry-like ways. When theoretical physicists talk about building spacetime from entanglement, the operational meaning of that phrase will increasingly be tested in quantum networks and simulators. Finally, it's useful to keep a modest, practical mindset. The kinds of time travel that make for great fiction, go back and fix a mistake, snatch a lost loved one from a doomed fate, collide with deep physical, thermodynamic, and informational principles that aren't easily bypassed. The math will keep offering neat wrinkles, and the physics will keep demanding respect for constraints. Our job as investigators is to let curiosity lead, but also to follow where experiments and logical consistency take us. That route has already produced striking insights. The role of entanglement in shaping geometry, the way semi-classical contributions preserve information in black hole evaporation, and the realization that everyday technologies like GPS live on relativistic principles. Along the way, we build tools and knowledge that matter regardless of whether a grandfather paradox ever shows up at our door. If you enjoy playing with the implications yourself, try this simple exercise. Imagine an idealized traversable wormhole the size of a car, and then, one by one, impose realistic constraints. First, require that all the matter holding it open obeys known quantum inequalities. Next, require that vacuum fluctuations don't diverge near the throat. Then demand that the construction could have formed dynamically from normal collapse or be built from finite resources. You will find the door rapidly narrows. Doing that mental bookkeeping helps you see why most physicists are comfortable saying the mathematics allows time machines, but that physics, including quantum field effects and practical resource limits, makes their realization extraordinarily unlikely. It's an effective way to keep the wonder of the idea while staying honest about the physics. Where the inquiry goes next is both experimental and conceptual. On the experimental side, push the semi-classical regime, grow coherent macroscopic quantum states, refine gravitational wave and lensing searches, and expand networks of clocks and quantum sensors. On the conceptual side, keep refining the relationships between entanglement, geometry, and information. Understand better how semi-classical backreaction behaves in near-CTC situations, and flesh out how computation and causality constrain each other. Those twin tracks, experiment and theory, are exactly the productive tension that advances physics. They will not only tell us whether wormholes and CTCS are practical, they will also shape our deeper understanding of space-time, information, and what it means for reality to be consistent. Pick up that mental experiment again, but this time be brutally concrete. Suppose you somehow get a microscopic traversable wormhole into existence, a tiny throat, maybe the size of a proton, stabilized for a microsecond. What could you actually do with it? The first thing to notice is that what you can do breaks into two very different categories: move matter, people, probes, particles, or move information. Moving a macroscopic object requires a huge, coherent deformation of spacetime and the ability to protect that deformation from every known kind of instability. Moving quantum information can be done with far less. A delicate pulse of negative energy, a careful coupling, and the right entanglement setup might let a qubit slip through. This distinction is the practical hinge of the whole conversation. Physics is surprisingly generous when it comes to letting tiny, fleeting, information-carrying maneuvers happen under special conditions. It becomes stingy to the point of forbiddance when you ask it to carry atoms, let alone people. Why is information easier? Because quantum mechanics already lets you encode, scramble, and transmit information in ways that don't require bulky, classical resources. Think about quantum teleportation. You don't physically move a particle from New York to Tokyo. You use entanglement and 2 bits of classical communication to recreate its state somewhere else. In some of the most exciting theoretical constructions, those ADS/CFT wormhole protocols, the bulk geometric picture makes this look like sending information through a wormhole when, in the dual field theory, you're just doing teleportation with a special coupling. The lesson is that geometry and information are interchangeable descriptions in some contexts. The catch: these tunnels for information are tiny, fragile, and tied to very specific boundary conditions. They're not doors you'd stick a person through. This is where operational limits come back in. Even if you could make a quantum wormhole that admits information through, you run into the no-signaling principle and thermodynamic bookkeeping. Quantum correlations can be weird and non-local, but you can't use them to send a controlled message into the past in a way that would violate causality at the macroscopic level. at least not in any model that plays nicely with the rest of quantum theory. Experiments like Wheeler's delayed choice or quantum eraser setups sometimes make it look as though future measurements influence past behavior. But when you unpack what's actually measurable, there's no way to use that effect to send a message backward. The correlations only become apparent when you compare data from both sides. You can't, by choosing a measurement on your end, force a definite change in distant past, outcomes that someone else could verify then and there. That's why retrocausality in quantum experiments is usually a story about correlations, not about controllable communication into yesterday. There's a similar flavor to the computational arguments. A fascinating line of theoretical work asks, if closed time-like curves, CTCS, were available even locally as a resource, how would that change what computers could do? Several toy models, including Deutsch's formulation of quantum time travel and other post-selection-based schemes, show you could solve very hard computational problems if you could interact with a CTC. That's an enormous red flag for nature to swallow lightly. The computational landscape, what's easy and what's hard, is not a random artifact. It's connected to deep features of randomness, information, and physical law. If a physical process collapsed complexity classes, we'd expect to see it reflected in everyday capabilities, clever algorithms, or at least technological signatures. We don't. So the fact that CTCS would be a computational superpower is a cautionary sign that something in the pile of physical laws will likely keep them out of reach. Another very physical constraint comes from stability and radiation. Imagine you've opened a small throat that connects two regions of spacetime. Anything moving through or near that throat will scatter quantum fields, produce radiation, and disturb the geometry. These disturbances tend to grow because the throat geometry can act like a resonant cavity for quantum modes. Semi-classical calculations frequently show these modes piling up around would-be Cauchy horizons, the boundaries beyond which predictability breaks down, and that pileup increases the local energy density. When energy density rises, gravity responds by altering spacetime, very often in a way that seals off the dangerous region. You can picture it like pushing a swing. If you push in tune with the swing's natural mode, you get a large amplitude quickly. Here, the natural modes of the quantum vacuum can resonate with the exotic geometry, and the push comes from the geometry itself. The result is back reaction that tends to shut down the configuration. These semi-classical results are not absolute proofs. Only a full quantum gravity calculation could be definitive, but they're consistent and persuasive enough that most researchers take them seriously. That brings us to the role of thermodynamics and entropy, which is both conceptually rich and practically important. The arrow of time, the reason we remember the past but not the future, ties to entropy. Messing with the past doesn't only require changing a localized event, it requires changing the records and memories that are spread through the environment. Those records are physical. They're fossilized correlations, broken eggs, worn shoe treads, seared atoms in brain tissue, photons scattered across the sky. When you think of changing the past, you're proposing to rewrite not just a single fact but a vast web of correlations that constitute the past's fingerprint. That's energetically and informationally expensive. To undo or alter a past macroscopic state would typically mean lowering entropy somewhere else to compensate, an operation that seems to get more and more costly the larger and more macroscopic the change is. In short, thermodynamics and the ubiquity of records make macroscopic retrocausation fantastically resource-hungry. You can see this with a simple, everyday example. If you drop a glass and it shatters, the shards and the spread of the pieces, the sound, the film loop on a phone, those are a distributed record of the event. Reversing that event in any localized patch requires gathering up and reordering an enormous amount of microscopic information. Every shard needs to be placed back, each scattered photon must be recombined, each tiny scrape on the floor erased. That's an entropy-decreasing operation. On the other hand, sending a single qubit back through an engineered microscopic channel corresponds to altering a minimal, highly controlled record. So the thermodynamic cost of macroscopic changes is a pragmatic impediment to building do-over machines. Let's talk about observational constraints. If large-scale time manipulation, traversable wormholes, or freely connective topology were common, we'd expect to see some astrophysical fingerprints. Traversable wormholes would lens light in telltale ways. They'd create unusual multiple-image patterns, ring structures with odd time delays, or brightness asymmetries that don't match ordinary lensing by galaxies or black holes. People have scoured lensing surveys and gravitational wave catalogs for anomalies that could signal exotic compact objects or non-standard topologies. So far, intriguing blips occasionally pop up, but closer inspection tends to show they're either instrument artifacts, analysis choices, or ordinary physics stretched by misinterpretation. Gravitational wave detectors are also sensitive tools. Mergers of exotic objects would produce waveforms with echoes, phase shifts, or ringed-on behavior deviating from the classic black hole templates. Searches for echoes have produced contentious claims, but nothing definitive. These null results aren't conclusive proofs that exotic objects don't exist anywhere, but they do put meaningful bounds on how common or how conspicuous such things can be. There's also the "where are the time travelers" style of reasoning. It's not a rigorous exclusion, but it's suggestive. If time travel into the past were feasible and practical, it's natural to suppose someone or some civilization might have tried it, unless there are compelling reasons preventing it. The silence of the sky and of human records is a kind of data point in favor of strong chronology protection. That doesn't mean every logically possible species of time travel scenario is impossible, only that large-scale or frequent episodes of macroscopic retrocausation don't appear to be out there in the local universe we can observe. On the theoretical front, the most hopeful glimmers come from two directions that are, in a sense, complementary. One is the increasingly precise toy models in quantum gravity and holography. These let theorists test how information and geometry interplay under controlled conditions. The Gao-Jafferis wall traversable wormhole and related constructions show that quantum effects can make tiny windows of traversability possible in special settings. The other is progress on the black hole information paradox, where tools like replica wormholes and entanglement entropies have given concrete mechanisms for preserving information without obvious causal paradoxes. Those advances hint at a consistent story. Geometry and quantum information conspire to encode and recover information without making paradoxical causal loops easy. In other words, wormhole-like structures show up in the calculations, but they're used to reconcile information flow, not to build grandfather paradox devices. A different, fascinating angle is the idea that time and geometry might be emergent from quantum entanglement. If space is a kind of network of entanglement between degrees of freedom, then manipulating entanglement patterns changes geometry in principle. That suggests a route to effective shortcuts for information. Instead of carving tunnels in spacetime, you manipulate the underlying entanglement architecture so information takes a different route. This is the spirit of ER equals EPR. Entangled pairs are dual to non-traversable wormholes. The duality is not a literal engineering manual for constructing wormholes. It's a deep statement that geometry and quantum information are two faces of the same underlying structure. The implications are profound because they recast questions about causality in the language of information flow. If causal constraints are encoded in entanglement structure, then changing causal relationships becomes a problem of changing entanglement, something that quantum information theory can treat precisely. But again, the upshot so far is conceptual insight, not a one-step method to send email to 1995. Let's return to laboratory reality to ground this. What experiments are worth watching if you care about the question of chronology protection? Three main fronts look promising. First, atomic clocks and precision timing continue to improve. If clocks keep getting better, They'll probe gravitational time dilation and relativistic effects on ever smaller scales. Any unexplained deviations would hint at new physics in the semi-classical regime. Second, optomechanical and levitated mass experiments are pushing the frontier of quantum superposition to more massive objects. If gravity resists superposition in some way, say, via collapse models, those experiments could reveal it. The outcome matters. If gravity behaves classically against quantum superpositions, that would change how we think about spacetime's quantum properties. If it doesn't, then quantum gravity must reconcile a fully quantum spacetime with causal consistency. Third, analog gravity systems let us test semi-classical behavior in controlled settings. Experiments with Bose-Einstein condensates or nonlinear optics can mimic horizon physics, mode mixing, and even basic features of Hawking radiation. They won't build a time machine, but they can demonstrate whether exotic geometries generically lead to runaway back reaction in accessible setups. Another practical direction is to develop more precise ways to look for wormhole-like lensing or exotic compact objects in the sky. The combination of wide-field surveys, like the Vera C. Rubin Observatory, high-resolution radio interferometry, and gravitational wave detectors gives a multi-messenger toolkit. If any truly bizarre lensing or waveform anomalies turn up, we'll have many independent ways to test them. That's how physics usually gets surprised, not by verifying a fanciful speculation, but by finding a persistent anomaly and insisting it be explained. So the search continues, and it's important because the absence of evidence strengthens the case for chronology protection. The presence of evidence would upend the foundations. Let's switch gears to the human and philosophical dimension, which matters a lot because time travel thought experiments force us to interrogate what we take for granted. The block universe picture, where past, present, and future are equally real, makes time travel less metaphysically puzzling. Moving around in the block rearranges which slice of world line you occupy. For many physicists, that's a natural picture because relativity treats time as another coordinate. But for our experience of memory, agency, and decision-making, that block view can feel reductionist and unsatisfying. Other philosophers prefer self-consistency principles, like Novikov's, which say that if closed time-like curves exist, events along them must be self-consistent. That sorta reconciles free will with paradox avoidance. You can act, but only in ways compatible with the already extant history. Quantum approaches add the possibility of branching histories, many worlds, or fixed-point self-consistency, where probabilities settle in a paradox-free way. These moves are more than metaphysics. They shape what types of models one considers physically sensible, and thus what experiments one should design. Ethics and law become urgent if you imagine practical backward causation. Suppose you could send information to your own past in a way that might alter outcomes. What are the responsibilities? Which versions of history are morally relevant? These questions start to look like real policy problems if we ever get even modest forms of controllable retrocausation, say, sending a small amount of information into a past light cone. People have thought through toy cases, grandparent paradoxes, bootstrap paradoxes where information emerges from nowhere, and they find that physics alone doesn't resolve all moral intuitions. That's why interdisciplinary work between physics, philosophy, and law matters even now. Pushing at the boundaries of causality forces us to think clearly about how we'd govern such capacities should they ever become feasible. So what's a fair, honest takeaway? The equations of general relativity admit geometries with closed time-like curves and wormhole shortcuts. Quantum theory offers mechanisms that sometimes permit tiny, controlled changes to causal structure in special contexts. But the full suite of constraints, quantum inequalities preventing sustained large negative energy, semi-classical backreaction, that tends to destabilize would-be time machines, thermodynamic and record-keeping costs for macroscopic changes, and the lack of observational evidence for macroscopic causal anomalies, combine to make practical backward time travel extraordinarily unlikely with our current understanding. That's not a grim finality, it's a research program. Each piece of evidence that tightens or loosens these constraints teaches us something deep about quantum gravity, about the nature of information, about how spacetime is stitched together. Looking ahead, there are neat, concrete things to watch. If levitated mass quantum superpositions show no anomalous gravitational decoherence, that will strengthen the case that gravity can be fully quantum mechanical, which in turn forces theorists to face the question of how a quantum spacetime handles causal paradoxes. If analog gravity experiments consistently show runaway back reaction in configurations mimicking CTC formation, that will bolster chronology protection arguments. If astrophysical surveys or gravitational wave observations ever find a lensing pattern or waveform inconsistent with standard compact objects, that will be a clarion call to revisit exotic topology scenarios with new seriousness. If quantum networks at scale start revealing ways to move quantum information that have clean, geometric duals, the practical meaning of building geometry from entanglement will become clearer and possibly more technologically relevant. And finally, the value of these investigations isn't only about constructing a time machine. Thinking hard about time, causality, and information has already produced concrete advances, tools and ideas that show up in quantum computing, precision metrology, and even in how we interpret black hole evaporation. The research program forces physics to be precise about what counts as an allowed process, what counts as a resource, and how different domains, gravitation, thermodynamics, quantum information, speak to one another. That cross-pollination is where real progress often comes from. So yes, time travel is real in the modest, tested sense that motion and gravity alter the passage of time and that we can exploit those effects. The bolder claim that you can routinely stroll into your own past and change events runs headlong into a thicket of constraints drawn from quantum inequalities, semi-classical instability, entropy, and observational absence. Physics hasn't closed the book. It's written increasingly sharp margins. The most likely scenario, given what we know, is that nature either outright forbids macroscopic, paradox-generating time machines, or restricts them to extremely exotic, highly constrained regimes where paradoxes are resolved by self-consistency, decoherence, or branching histories. Either way, the inquiry is far from wasted. It pushes us toward a better understanding of space-time, information, and the deep, sometimes surprising rules that hold the universe together. If you want one practical next step as an interested person, follow the clocks. That's where the rubber meets the road. New generations of atomic clocks and distributed timing networks are the most direct and empirical tool we have for probing how time behaves when pushed to extremes. Watch the papers about levitated optomechanics and tabletop gravity experiments. Keep an eye on gravitational wave detectors and wide-field lensing surveys for anomalous signatures. These are the places where theory and measurement will have the decisive conversations. As for the romance of time travel, of returning to fix a mistake or to eavesdrop on your childhood, that remains in the realm of fiction for now. The scientific story is, in its own right, richer and more interesting. It's about how causality, information, and geometry interweave, and how the universe protects its own history while still leaving room for the small, surprising ways that time bends and stretches under motion and mass.